Hello class, this is a video tutorial on sets, sample space, and basic probability. The same concepts from previous years still apply, but the notation will be different and a few more concepts will be added or extended. Let's begin. Sets. A set is any group or list of things that fit a description. The sample space is a set, or it lists all the elements of a probability experiment. Elements is just a special name given to things that belong in a set. Sets and probability can be visualized using Venn diagrams, among many other things, but we'll be using Venn diagrams pretty frequently in this video. So for example, let's say we have the probability experiment of throwing a six-sided die. So we roll it. So the sample space, denoted as S, and this is the notation for set notation. We do a little squiggly bracket here. And the elements that belong to this description, six-sided dice is rolled, are the numbers 1, 2, 3, 4, 5, and 6. So this is the sample space of a six-sided dice being rolled. For the Venn diagram, since this is everything that could possibly happen in this particular probability experiment, we just list them as 1, 2, 3, 4, 5, and 6. So inside this box is everything that could possibly happen. It's just the numbers 1, 2, 3, 4, 5, and 6. We can further narrow down the set. So we can say that the set A are just even numbers. So we can narrow this down. So A are just the even numbers. So 2, 4, and 6. We can visualize this using a circle. Label this A and list numbers 2, 4, and 6. We can do a different one example here. We'll do the set B are the multiples of 3. We'll set B, we can say multiples of 3 within this particular probability experiment. Well, that's only 3 and 6, which we can also list as this. So this is the set B, it's 3 and 6. So this is us listing the numbers individually within the Venn diagram. But in future, what we'll be doing is rather than list them individually, as I've shown you here, inside the Venn diagram, we're going to instead count just the number of elements in the Venn diagram and write that in the Venn diagram itself. So for example, this has 2 elements. So rather than write 3 and 6, we'll just write 2. Set A has 3 elements, 2, 4, and 6. So rather than write 2, 4, and 6, we'll just write 3. And same goes for this one. Rather than write 1, 2, 3, 4, 5, 6, we have 6 elements, so we'll just write 6 on the outside, like so. The magnitude, this is actually what we've just done, of a set is the number of elements contained in that set. It's got the notation, absolute value. It kind of looks like that, but vertical lines with the set letter inside of it is just the number of things inside of A. You might also see it in this notation, n bracket A, so the number of A, or this one here in modern notation or modern vernacular, we call this the hashtag. It's really the palm key or hash. It's just hash A. And these 3 notations are exactly what we've just shown here. So in this case, I'll do all 3 notations. So the number inside S is 6, or the number inside A is 3, and the number of things in B is 2. I've shown you all three notations. You pick one and keep it consistent in that way. Okay, so now let's do some calculations. And or conditions. The probability of 2 or more events can be considered and are calculated as. So here we go. So when we read the word and, we only count common elements. In set notation, this is referred to as an intersection and is visualized as follows. So going back to what we saw, so this is A intersect B, or it can be written as A and B. So we saw before that set A are the even numbers 2, 4, 6. Set B are the multiples of 3, 3 and 6. The set A intersect B, we only count the common elements. So in this case, 6 is found in both lists. So 6 is here and 6 is here. That is the only common element. Therefore, A intersect B is the only element 6. Visualizing this intersection visualizes that number 6. There's only one number in this one here. So remember, rather than write the number itself, we write the number of things in that element, which means B, this section here, is representing things that are only in B and not shared with A. So originally there were 2 things inside B, but now because one of those things is shared with A, we write only 1 here. Because now 1 plus 1 gives us 2 things inside of B. Same goes for this. There are 2 more elements that are only inside of A. Now if we count these numbers, 2 plus 1 plus 1, that gives us 4, which means there are 2 more numbers that don't belong in A or B. So we write a 2 on the outside, indicating that there are 2 numbers that do not belong inside set A or set B. So that is the AND condition. The OR condition. The OR condition means to combine both sets without counting common elements twice. In set notation, this is referred to as a union and is visualized as follows. So A union B, written as A or B. So for example, same numbers as before. If A is 2, 4, 6, B is 3, 6, A union B is, we're going to combine both of these. So if we combine this, it'll be 2, 4, 6 from A, and then 3, 6 from B. However, because 6 has already been counted, we make sure that we don't count it again. So in actual fact, we need to erase one of those 6s. And this here is the union of A and B. As you can see, this is a visualization of it as shown. So it's everything in A and everything in B, even their intersection in the middle. Combining all of this, we can calculate basic probability of any event or outcome occurring is as follows. So the probability of X, where X is any description that we want or any set that we want, it's the number of things inside of X divided by the number of things in total in the sample space. Let's do an example of this. A fair 6-sided die is rolled. let's list the sample space. We've already done this before. S is given as 1, 2, 3, 4, 5, and 6. We can count this as the number, the number in S is given as 6. Let the set X be all numbers less than 4, and set Y be all numbers, let set Y be all odd numbers. Let's list each set, and let's calculate the probability of X and the probability of event Y. So X, listing these, it said all numbers less than 4. So it's going to be 1, 2, and 3. The probability, the list of Y, all odd numbers. All odd numbers are 1, 3, and 5. So that the probability of X, given as the number in X over the total sample space, which is 6. But the number of things in X are 1, 2, and 3. And now I'm going to really into a lot of detail of this. 3 over 6, which we can simplify to be half. Probability of Y is the number of things inside of Y divided by the number of things in the sample space. But we've already calculated that the sample space has a total of 6 things, and Y has a total of 1, 2, 3 things. Also 3 out of 6. Illustrate the sets as a Venn diagram and calculate the probability of X intersect Y, and P, the probability of X union with Y. Okay, so let's illustrate this. Here's my sample space. Let us draw a circle. No fill for this one. So we know it's going to intersect like this. Let's let this be set X, this be set Y. X would be 1, 2, and 3, so there should be 3 things in total here. Set Y should also have 3 things, but looking very carefully, there are shared values. So in the intersection here, there are 1 is shared and 3 is also shared. So there are 2 things that belong in the intersection, so 2 goes into the middle, which means we have to subtract from the left and right. So from X, there should only be 1 here and 1 here. So 1 plus 2 plus 1 gives us 4, which means 2 things are not listed, which go on the outside here. Well, from just looking at the Venn diagram now, probability of X intersect Y, the intersection is here in the middle. It's 2 out of 6, which is 1/3. The probability of X union with Y, it's everything in here. So 1 plus 2 plus 1 is 4. 4 out of 6, which is 2/3. So, hope that gave you an insight into this new notation, as well as the intersections and the union of sets. Hope to see you in the next video. Best of luck.